This is lab 4 for physics 2, the magnetic field of permanent dipole magnets. The purpose of this lab was both to measure the distance dependence of the magnetic field due to a small bar magnet and to compare measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. There are two major physics concepts involved in this lab. The first was the distance dependence of a magnet, which states that the magnitude of the magnetic field due to a bar magnet is going to be equal to some constant times the distance from that bar magnet to some power. And then the Biot-Savart law for magnetic dipoles, the equations of which are in the bottom corner here. Here are the materials we used in our lab. We used a bar magnet, smartphone, 2-meter sticks, a magnetometer app, a few pieces of tape, and an Excel spreadsheet associated with this lab. Here's our lab setup. We first compensated for the presence of Earth's magnetic field by orienting the phone so that the x-component equals 0, and this ensures that Earth's magnetic field is going to be orthogonal to the measured experimental values, and so it minimally affects our results. We then located we found the location of the magnetometer inside of the phone by lining it up with on axis with the bar magnet, and then just sliding the phone up and down until it reached a highest magnetic field recording in some component, and then we knew that was where the magnetometer was. Here's our recorded data. Here's our data graphed by natural log of distance and natural log of the x-component of the magnetic field. And then from that data, we were able to establish a linear relationship. We found that the distance dependence was the slope, which is about -3. And then k is going to be e to the y-intercept, which is going to come out to be about 5 times 10 to the -7. And then here's our calculation for the magnetic moment, which came out to be about 5 amps times meters squared. We then measured some point on the off-axis field, plus 2.2 meters horizontally and plus 0.2 meters vertically from the magnet. Here are results from that, and we had to correct for the Earth's magnetic field in the y direction. Here's our computational model, which we measured. We set the magnetic moment of this magnet here in our model equal to our calculated value, and then we measured the magnetic field at the equivalent off-axis location that we measured here. That came out to be about 7 times 10 to the -6. The differences in results were likely due to a few reasons. It could either be due to interaction in the phone's magnetic field measurements, influence from Earth's magnetic field, influence from other magnetic fields. Any one of these reasons, if it was true, would influence the results in our calculations. What if we hadn't oriented our experiment to compensate for magnetic north? Our results would have been influenced by the Earth's magnetic field, and each result we would have would be the magnetic field due to the magnet plus the magnetic field due to the Earth. This made the resulting calculations inaccurate. What if we were to stick two identical magnets together? We would have gotten about double the result for each observational measurement because the magnetic field is now due to a dipole with double the moment of the original. In conclusion, we measured the distance dependence of the magnetic field due to a small bar magnet to be -3 in accordance with the dipole field model, and the discrepancy between our predictions from the computational model and our measured results was likely due to errors following the lab procedure.